All right, let's dive right into this explainer, focusing entirely on a highly structured expert blueprint of Domain 3's system architectures. If you're preparing for the CISSP exam, you already know Domain 3 is a massive beast. It covers everything from the micro level of CPU execution all the way out to macro level cloud-based microservices. Well, I'm here to be your instructor and guide to help you master this material. Together, we're going to decode the specific traps, architectural models, and engineering principles you absolutely must know to pass.
Here's our roadmap for today's explainer. 1. Hardware and CPU execution. 2. Memory types and security. 3. OS protection mechanisms. 4. Industrial and distributed systems. And 5. Virtualization and modern architecture.
Section 1. Hardware and CPU execution.
Okay, we're starting at the very foundation of computing. But before we even crack open a physical chip, we have to talk about the overarching legal and contractual reality that governs modern systems. The crucial point here is that organizations simply do not operate in isolation anymore. Because we all use common operating systems, standard network protocols, and third-party cloud providers, security demands diligent, shared responsibility between you and your vendors. Here is your first CISSP exam mindset note. When you see questions about cloud providers or off-the-shelf software, remember this rule. You can outsource the execution of a service, but you can never, ever completely outsource the responsibility for your data's security. That burden is a legally and contractually shared one.
Now let's look at how the CPU actually executes code. The exam absolutely loves to test these execution types against each other. Think of multitasking kind of like juggling with one hand. A single-core CPU is pseudo-simultaneously managing multiple tasks, but it's only truly touching one in any given exact microsecond. Multiprocessing, on the other hand, physically harnesses the power of multiple processors or cores. It literally adds more hands to do the heavy lifting simultaneously. And just as a quick aside, some systems even dedicate specific tasks to specific CPUs. That's a concept known as affinity.
Let's unpack the next major distinction: multiprogramming versus multithreading. CISSP exam mindset note: do not get tricked by this on test day. Multithreading happens entirely within a single parent process to keep overhead low. It's incredibly efficient because it totally avoids full context switching. Multiprogramming, however, is a way the OS batches entirely different tasks, literally saving the state of one program when it stops for I/O and starting up the next completely different one in line. Moving on to Section 2, Memory Types and Security. Now that we understand how the CPU executes code, let's see how it accesses and secures the data it needs to process. There are 5 core memory addressing schemes you really need to categorize for the test. Register addressing, that's lightning fast because it happens right inside the CPU's arithmetic logic unit. Immediate addressing requires no memory lookup at all because the data is hard-coded right there in the instruction. Direct, indirect, and base plus offset all involve actually going out to find the memory location. Pay special attention to indirect addressing. That's where the CPU is given a pointer. It's an address that simply holds the address of the actual data. But what happens when we store data permanently? Well, we have to worry about data remanence. You know, the digital traces left behind after you hit delete. Time for another CISSP exam mindset note. If you get tested on solid-state drives or SSDs, you must remember that traditional zeroization wipes are often totally ineffective. Why? Because SSDs use built-in wear leveling. They spread writes across the drive to prevent failure, which actively stops a utility from directly overwriting specific bad blocks. And since drives can just be physically stolen out of a machine, full disk encryption is an absolute must-have control. Stepping away from the storage media itself, we literally have to think about physical emanations. Even basic everyday hardware like monitors, keyboards, and network cables leak electromagnetic radiation. Attackers can actually intercept these signals using a technique called Van Eck freaking to read your data right out of thin air, which of course leads us to our required countermeasures.
So you definitely must memorize these 3 specific TEMPEST countermeasures. First, a Faraday cage. This physically blocks signals using an external metal skin. Second is white noise, which is a logical countermeasure that broadcasts false, useless traffic to just drown out and mask the real data. And third, if you combine a Faraday cage with white noise in a specific, contained area, you've created a control zone. Make sure you know these definitions inside and out.
Section 3, OS protection mechanisms. Stepping up from the hardware and memory, let's examine how the operating system secures its runtime environment against malicious or buggy code. An executed process follows an exact life cycle, basically acting as a state machine. It starts in the ready state, just waiting in the queue.
When its time slice arrives, it moves to the running state on the CPU. Now, if it needs to wait for a network request or a disk read, it steps over to waiting. Once it's finished, or if it's terminated by an error, it hits the stopped state, where the OS recovers its memory. Grasping this flow is totally critical for understanding how an OS manages resources securely. To protect those processes from stepping on each other's toes, OSs use a protection ring model. Ring 0, which you'll also hear called kernel mode or privileged mode, is the absolute core of the OS. It has full preemptive access to every single resource. Out on the edge, we have Ring 3, or user mode, where all your regular applications run. Here is a very important CSSP exam mindset note. A classic test trap is reversing these privileges. You must actively remember that the lower the ring number, the higher the privilege level. Ring 3 applications have to make mediated system calls if they want to ask Ring 0 to do anything sensitive.
Section 4, Industrial and Distributed Systems.
We're zooming way out now from individual computers to look at macro-level operational technology and massive industrial controls. Just like a lighthouse watches over a vast, sweeping coastline, supervisory control and data acquisition, SCADA systems, act as guiding beacons. They are designed for data gathering and event-driven oversight across massive physical geographies. Think power grids or regional water distribution networks.
You really need to know the hierarchy of these industrial systems. At the foundational level, a programmable logic controller, or PLC, is a focused computer controlling just one single mechanical device. If you network a bunch of PLCs together inside a single factory, you get a distributed control system, or DCS. And if you connect multiple DCSs across a whole state or country, you have SCADA. CSSP exam mindset note. Memorize this exact scaling distinction. And remember your due diligence requirement here. These are legacy systems. They were almost never designed with inherent security in mind, and patching them without causing real physical world downtime is incredibly difficult.
Over on the IT side of distributed systems, we have grid computing. This loosely groups processing nodes together to tackle massive, complex calculations like protein folding or climate modeling. While this kind of parallel processing is amazing for public scientific research, the core security flaw you've got to recognize is that the processing nodes are untrusted. Because work packets are just blasted out to the world, grid members can easily keep copies of the data. Therefore, grid computing is entirely unsuitable for private, confidential, or proprietary data, no exceptions.
And finally, Section 5, Virtualization and Modern Architecture.
Let's explore how modern abstraction has absolutely revolutionized data centers and deployment methodologies. Virtualization relies on a hypervisor, right? The virtual machine manager. It's critical to know where this hypervisor sits. A Type 1 hypervisor is bare metal. It installs directly onto the hardware itself, completely eliminating the need for a host operating system. This makes it incredibly efficient and secure for massive enterprise server farms. Now, a Type 2 hypervisor is hosted. It actually requires a standard operating system like Windows or Mac OS to run underneath it. That's great for sandboxing on a user's desktop, but really not ideal for large-scale enterprise deployments because of all that extra OS overhead.
Which brings us to one of the most important shifts in modern cloud engineering: infrastructure as code and immutable architecture. We now manage hardware configurations exactly like we manage software code, using version control. And we treat our servers as cattle, not pets. What does that mean? Well, if a server breaks or needs an update, we don't carefully nurse it back to health midstream like a beloved pet. No way. We simply destroy it and use automated templates to spin up a perfectly consistent, brand new replacement. This completely eliminates configuration drift.
I'm going to leave you with this final thought provocation as you continue your CISSP studies. Do you know the exact difference between elasticity and scalability? Elasticity is a hardware or platform characteristic. It's the ability to dynamically expand or contract resources to instantly meet changing demand. Scalability, however, is typically a software characteristic. It is the application's inherent design ability to take on larger workloads. Do not confuse these two on exam day. Understanding this exact nuance is an absolute key to conquering Domain 3. Keep studying hard, stay focused, and use these blueprints to lock in your understanding.